Okay, this is our first lesson in thermodynamics. So as we start this new unit, what we're going to do at the beginning here before we get to really our learning objectives in this lesson is just kind of set the stage for why are we studying thermodynamics. And it turns out the reason we're studying thermodynamics is going to be the same reason we're studying equilibrium and electrochemistry. It really starts us down a path of looking at how energy can be a very useful tool in thinking about chemistry. So let me give an example. Here's my example. If we have a reaction, you look at this reaction and I say to you, oh, well, clearly this is a single displacement reaction. What would be the products? And very often you look at that and you go, I know what the products would be. I would do a little metathesis, a little switching out, and I get some calcium and some aluminum carbonate. But the big question here is, just because we could draw down the products, would we actually get those if we went into lab and took a chunk of aluminum foil or something like that and some solid calcium carbonate, mixed them up in water? Would they actually produce a product? And it turns out the answer is, well, sometimes and sometimes not. And what thermodynamics is going to do is at the end of the unit, it's going to boil it down to one value called free energy, which is abbreviated delta G. Now, you don't need to write this down right now because this is the culminating part of the unit way at the end. And more or less, if delta G turns out to be negative, 20 kilojoules or any number of kilojoules, that's going to tell us that the reaction is very spontaneous, that it happens naturally. So yeah, we can go into lab and we can do it. But if delta G turns out to be a positive sign, and of course the more positive that number is, then there's really no point in going into lab. It's not going to work unless we put a lot of energy into it. So that's the culminating goal here, is being able to predict if reactions will occur in a very natural and spontaneous way. It can save you a lot of time in lab if you know the answer to that. So how are we going to do this? Well, in a nutshell, two more things you don't need to write down right now because we're going to spend all of the unit looking at them, is if you want to know what the free energy is of a reaction, it's not so simple because free energy is actually made up of two things. One is enthalpy, delta H, and the other is entropy, delta S. Now, these are two different forms of energy. It turns out energy flows back and forth between these two different forms, hence the reason why it's called thermodynamics, right? Dynamic meaning, moves, I suppose would be a great way to say that. So if you were going to look at the unit as a whole, figuring out what enthalpy is going to be the point of the first week or so, week and a half of our studies, and that's in chapter 6. And entropy and the act of how we bring these two together to figure out the free energy of the reaction is part of chapter 17, and that's sort of the last half, the last week and a half of this unit. So that's what we're after. How can we use a little bit of math and understanding of energy to figure out if reactions will occur spontaneously? Now, that's not where we're going to start, though, because this is thermodynamics, right? You can hear it in the thermo part. This is the study of heat transfer. Now, that is a good description of what delta H is, but it's not a very good description of what delta S is. So today we're going to be leading into what delta H is. You're not going to hear delta H today. That's coming up a little bit later, but we're leading down the path of how heat plays a key role in all of this. All right, so this is our introduction to heat transfer. We're going to bridge from some things that I think you know to some other things that maybe will be new to you. I'm setting the book down, by the way. Chapter 6, Chapter 17, in zoomed off. Okay, let's get to it. So what are we going to do in this lesson specifically? We're going to be able to predict the direction of energy flow, identify the system and surroundings because those are key terms for chemistry, determine the sign, whether it's positive or negative, of that energy flow. You saw that delta G had a sign that was going to be very important. Well, today we're going to lay the groundwork of the meaning of those signs. And lastly, be able to identify the flow of energy as endothermic or exothermic. Now, we introduced this last one in the previous unit, but we're obviously going to make sure that we feel pretty good about it here. Okay, so let's look at some heat energy. If you have a coffee cup, right, sitting on the table, obviously that coffee cup is pretty darn warm, right? And if you imagine putting your hand around this thing, right, you probably have a feeling for the direction of flow of heat because heat energy flows in a very specific direction. As a matter of fact, if you imagine your hand around that coffee cup, right, the coffee cup is the hot part, and heat energy always flows from the hot part to the cold part, which is, your hand. I think that seems pretty obvious. We imagine the particles moving really fast in the hot stuff, and they're moving slower in your hand. And essentially what's happening is the particles in your hand start to move a little bit faster as that heat energy flows from hot to cold objects. The symbol for heat is, oddly enough, Q, and it's a lowercase q. Super important. By the way, capital Q has a meaning in equilibrium that we'll find out about later. The unit for heat is one of two. There's the joule and there's the calorie. But know that AP really focuses on the joule, and as a matter of fact, the kilojoule will be far more important. But those two are probably the most common. But you'll see why calorie shows up a little bit later. All right, now, of course, if you have 2 units of energy, just like when you had 2 units of pressure, you got to make sure that you can convert between them. And the key conversion is that 1 calorie is equal to 4.184 joules. Now, I want you to write that down because I'm going to have you use it in a problem in a second. It might actually be in the problem. But in any case, it's going to be an important conversion in this unit. Okay, so if I have a candy bar, a Milka bar, I love these things. And, because these things come from Europe, I think Switzerland, maybe Germany. In any case, quite often in Europe, they give the energy value. In other words, if I'm worried about my diet, they give the energy value in kilojoules. And what I want to know is, I want to know how many calories would I be consuming if I ate this candy bar. All right, well, if we're going to do this conversion, clearly we've got to convert our kilojoules to joules first. 1 kilojoule is 1,000 joules. And then, of course, we had our conversion factor at 4.184 joules is equal to 1 calorie. And I get 536,000 calories. I mean, I do definitely need to watch my diet there, don't I? Because that is a shocking number of calories. I mean, wait a minute. Aren't we supposed to only eat like 2,000 calories in a day? Isn't that what they say? What's going on here? Well, if you didn't know, this is actually on a food package. It would say 536 calories with a capital. Now, in chemistry, we don't really do this, but nutritionists, when they say 536 calories with a capital letter, they really mean 536 kilocalories, right? So nutritionists, the way they write it's a little bit weird, but really if we ate this whole candy bar, it would be 536 kilocalories. So yes, if you converted it to kilocalories, you would see what they have right there in the nutrition bar, which, by the way, I deleted that because I wanted us to do the calculation. Yeah, so converting kilojoules to joules, converting calories to joules, and of course kilocalories to calories. Now, we're pretty good at unit conversion, so we're not going to do this too much, but I just wanted to bring that up because you're going to see that occasionally in this unit. Okay, so when heat flows, of course, it always flows from hot objects to cold objects. But the way we're going to designate this, if we say, okay, here's the hot object and the heat is flowing out, that means from the coffee cup's perspective, that's a negative flow of energy. And from your hand's perspective, that's a positive flow of energy. Whenever heat is flowing out, negative. Whenever heat is flowing in, positive. I think that makes sense. Now, of course, a way that I think about this is, if I said to you, hey, give me $50, I'd be like super pumped about that because that $50 is coming to me. How am I going to feel about that $50? Obviously, I'm going to feel pretty darn positive about that $50, but how are you going to feel about that? Well, if it's leaving your wallet, I'm betting you're going to feel negative $50 about it. And it's the same idea here. So perspective is really going to matter a lot, but that's the way we intend the use of heat here as well. Whenever heat flows out, negative. Whenever heat flows in, positive. All right, so if we're looking at these cute little kids here sitting there, what do you think the Q is for the kids here? Positive or negative? Well, definitely, assuming that we're talking about the heat from the fire, it's going to be going towards them. They'll be receiving it. It will be coming in, and Q will be positive. Of course, if you're the fire, the Q is negative. What about this? Let's look at what is the sign of Q for the ice cubes. Well, the ice cubes are cold, The water is warmer, I might not say hot. So therefore, heat flows from hot to cold, so it's going to go from there into the ice cubes. Since it goes from hot to cold and flows into them, the Q from the ice cubes perspective will be positive because the heat's flowing in. Now, of course, if you were talking about from the water's perspective, well, the heat is going from the water to the ice cube, so Q would be negative. Heat always flows from the warm or the hot to the cold, and if it's coming in, it's positive. If the heat's going out, it's negative. Of course, we could apply these terms to it as well, which is exothermic means heat is released, endothermic means heat is absorbed. We've already seen that, and of course, this cute little idea here that, you can hear the exit sign like to a room or something like that, or a highway. It means leave, right? So this is heat being released, and this is heat entering. Of course, that means that all processes that are exothermic, since the heat is leaving, are going to have signs of Q of, well, negative, because it's leaving. And of course, every time heat is entering and it's endothermic, Q is going to be positive. All right, so if we were looking at the kids again, the heat was flowing in, Q was positive. From the kids' perspective, this is a endothermic process. Okay? All right, so let's try this out. Here's just an example. A hiker puts a rock by the fire. I've actually never tried this, but I've heard this. You put a rock by the fire, get it nice and hot, and then you take it with you into your sleeping bag. And so when you're in there in your sleeping bag, from the sleeping bag's point of view, was the heat positive or negative? Was it endo or exothermic? Well, the rock was hot, the sleeping bag was cold. Heat always flows from the hot to the cold object. And therefore Q they said sleeping bag's perspective. Q is going to be coming into the sleeping bag, so it's positive. Yep, it is endothermic. Let's try another, let's see. So before we try another one, you can see that perspective really matters. For a minute there, I was about to talk about the rock because I said the rock was hot and this was colder, and you saw me about to put Q on the rock. Well, of course, he's leaving the rock. You'd say negative. You'd say exothermic from the rock's perspective, right? And that brings up the idea of system and surroundings. Well, you as a chemist or a researcher in any way have to define what the system is. That previous problem defined the system as the sleeping bag. I almost made the mistake of looking at it from the rock's perspective. So whatever the situation calls for is what we're going to define as the system. So in most of these examples, the answer depended on what we're focusing on. That's absolutely true. The object that is the focus of the scientist's interest is the system. As a scientist, you get to decide what that is. Now, of course, in chemistry specifically, that is always the chemicals in the reaction. So we said in the beginning, like aluminum would react with calcium carbonate. Both the reactants and the products that are made, this is the system. But not the solvent. You may have done that reaction in water, right? In other words, this would have been, actually both of these would be solid. But in any case, if you had these things dissolved, the solvent is not the system in chemistry. It's only the chemicals, because it's chemistry. Now think about this interesting situation. Is you can imagine that if you were interested in cars, right? The perspective the perspective that you have will depend very much what your job is, right? Like, for instance, if you're a person if you're a chemist who's designing a better battery for an electric car, it means to be a battery, well, then obviously the system here is the battery, right? But if you're an engineer that's meant to use the power in the battery to make the car go more efficient, then obviously the car would be the system, and the energy would flow out of the battery into the car. So a lot of times, if you go, this is just a little foreshadowing, the signs you learn in chemistry, very often if you go into engineering, you may find that they're switched because they're more interested in what the chemicals or the battery are powering. All right, so let's try a second practice. You're holding a cup of ice cream. If the ice cream is the system, is the heat flow positive or negative? Is it endo or exothermic? Well, let's label what's hot and cold. So the ice cream, I think, is cold. Your hand and all the rest of the stuff around it is warmer. Hot energy always flows from warm to cold. So therefore, the ice cream, if it's the system, is going to have energy coming in. So we know it's endothermic because the heat is entering it. And the heat flow coming in is positive from the ice cream's perspective. Let's try another one. If we have some molten iron, which just means iron metal that's been melted, right? It's not there's no water or anything, it's just iron melted, is poured into a clay container. If the molten iron is the system, as chemists would think it should be, is the heat flow positive or negative? Is it endo or exothermic? Well, here we have our molten iron. It is clearly hotter. The clay pots and everything around it are colder. That includes the air, that includes everything. So the energy is going to flow from the hot to the cold. They said the system was the molten iron. So therefore, from the molten iron's perspective, heat is leaving. It is exothermic. And because heat is leaving, the sign of Q is negative. All right, last one we're going to try. Practice 4. So if you have room temperature water, it's placed in a refrigerator. If the water is the system, so these things, what do you think the sign would be? Would it be endo or exothermic? Well, the water is the system. I think the water is warmer when you first put it in relative to the cold refrigerator. The walls are all cold. Because that's true, the heat energy is going to flow from the warm to the cold objects. Therefore, that heat energy will be leaving the water. It will be exothermic, and because it's exothermic, the heat is leaving. Just like when money leaves my wallet, I feel bad about that. It is going to be a negative heat flow. All right, great job. So that's our first lesson, just sort of laying the groundwork of thermodynamics. Because thermodynamics, you can hear the term thermo in it. It is about heat, and the flow of heat is going to be very important in this unit, at least the first half, where we're learning about enthalpy. Now, I didn't bring up enthalpy at all here, and as a matter of fact, we're not going to see enthalpy for a couple of lessons, but know that it's closely related to what we're doing here. All right, great job. Let's go to the next lesson.